Howdy, everyone, and welcome to the first online video for statistics. Today, we'll deal with confidence intervals for proportion, which is a continuation of the idea of confidence intervals that we finished the third quarter with. Later this week, we'll also talk a little bit about sample sizing for proportion. This will end confidence intervals, and next week, we'll begin talking about the other side of this, which is hypothesis testing. For now, though, let's talk a little bit about proportion and specifically how we handle confidence intervals for it. So first, first thing we might want to look at is what do we mean when we talk about proportion, when we talk about a population proportion versus a sample proportion. The main thing we talk about here is trying to predict a population using a sample, the same way that we did for sample means, the same way that we did for trying to pick whether a distribution was large enough for Z or not necessarily where we needed T. It's this idea that we have sample data that needs to imply something about a population. So here, our population proportion is P. This is the same P that we've used for proportion before, that we've used to mean probability, that we've used to mean pretty much anything that falls into a decimal percentage type of thing. We also use sample proportion being P hat. The same way that sample mean was X bar. So we calculate p hat as the amount of some sample that holds a quality we want over the total sample size. So we have X as that amount that has the quality we want, N is the total sample size, so p hat is just X over N. We also have that Q is the opposite of P, so Q hat is the opposite of P hat. So Q hat is equal to 1 minus P hat. So most of the time you'll either be given P hat or given Q hat, or most of the time you'll need to simply find it relatively quickly. So for example, here, when 200 people were surveyed, 162 said they like their haircut. So that 162 is that quality that we want, or that we're looking at for whatever reason. So we take 162 over our sample size of 200, and that gives us p hat, which in this case is 0.81. So great. This is how we're going to be setting up proportion. So let's figure out what that means for confidence intervals. So the thing with confidence intervals is that they're built around this idea of how much we expect to deviate from an expected value. Um, and and with mean and standard deviation, that was relatively easy to understand because mean is expected value and standard deviation is this idea of the kind of quote unquote standard difference from the expected value. So it was well understood or well defined. Here, it's not as clear that this is a simple idea of what the standard deviation is or what how we're moving. But we can refer back to something we did early in the third quarter to figure out how this works. And that is the normal approximation for the binomial distribution. Yeah, it shows up again. So here, the idea was that when we have when we have a binomial distribution that's large enough, it creates something that's like a normal distribution. And here our idea is that with a proportion, every single data point, every single person that responds to a survey, every single person that casts a vote, every single time we look at a fruit and go, is that an apple? We have something where we're saying essentially we're asking a yes or no question. So, and we're just recording how many times we get a yes answer. So here, that means that we're effectively creating a binomial distribution, a series of yes or no responses where we're just focused on how many times we get an affirmative, how many times we succeed, how many times we get a yes. So here, that means that it's reasonable to treat proportions like they're bound by the same rules that the normal approximation for the binomial, excuse me, that the normal approximation for the binomial distribution was bound by. So What that means is we once again need NP and NQ, or in this case, NP hat and NQ hat, to be greater than or equal to 5. Those were our somewhat arbitrary but reasonable starting points. Um, in this case, that's as simple as just X, our number of affirmative responses, and N minus X, our number of negative responses, both being 5 or greater, because then by definition, NP hat and NQ hat will both be greater than or equal to 5. So that's rather nice. And as a second thing, because we want p hat to be a good estimator, it's difficult for p hat to be treated like a normal distribution if the sample size is more than about 5 to 10% of the population size, because if it's too large, what ends up happening is we will follow whatever type of distribution the population follows, or will be subject to the same biases that the population might be subject to. Which sounds like a good thing and sometimes is a good thing, but for the purposes of actually creating confidence interval, it doesn't allow us to use this normal distribution. So, pretty difficult to actually have this happen, that your sample size exceeds 5 to 10% of your population size when you're dealing with proportion. Usually you're taking a proportion of just gigantic populations. So it's very difficult for this to happen, but it's just nice to know this general rule exists. This guideline is a better way to put it. This guideline exists. But the main thing here is that the standard deviation we're going to be using when we deal with proportions, the standard error more specifically, is going to be the square root of PQ over N, or more specifically P hat Q hat over N. This is the one we're more interested in. And this comes about quite nicely from that idea that we're trying to find a way to work with the binomial distribution, which had a standard deviation of root NPQ. Well, if you divide by n, which you've seen that we in creating kind of a in using our central limit theorem, this is sort of exactly what we're trying to do. When you divide by n, you end up with not root NPQ, but with PQ over n, all in a square root. Moving on to how we're going to build our confidence interval. Instead of multiplying by sigma over root n, we're going to be multiplying our z by root p hat q hat over n, as you'll see here. So an effective standard deviation of root p hat q hat over n, again, no need to divide by root n again, we already got it. We get a standard error of z sub alpha over 2, your z for the confidence interval that we've dealt with in the past. Z sub alpha over 2 times root p hat q hat over n. So our confidence interval, instead of reading x bar minus z sub alpha over 2 times standard deviation over root n, now it reads p hat, instead of x bar, minus z sub alpha over 2, it's the exact same z, times root p hat q hat over n. So, this ends up creating a lovely little comparison to our confidence intervals for the mean. Notice here, this is only z-score. We don't need to worry about t-distributions here, because if we're ever trying to use a t-distribution, that means that it's not really normal-like enough for us to be trying to treat this like a normal distribution, like a confidence interval in the first place. So we will, for proportion at least, for the purposes of this class, we will always use z. So, last rule of thumb, we should generally round to 3 places. Sometimes if we only round to 2 places, it won't be precise enough. This just gives us a nicer idea of what's going on. If nothing else, it looks a little cleaner. It looks a little more professional. It simply provides information that it's worth providing. So rule of thumb, round to 3 places. It's a good idea. Um, and once again, be careful with your arithmetic. There's a lot going on here in terms of places where you could make arithmetic mistakes. Um, if you're going to try and follow order of operations, if you're going to try and use a calculator that you can't just kind of write things in one string in and have it do order of operations for you, please do p hat times q hat over n first, find out what the square root of that is, then multiply it by z, and then take all of that and add and subtract it from p hat. Don't try and do this in one string. If you're not using a solid calculator, or if you enter it incorrectly, you will make a mistake and it will look really ugly. These are proportions. If you're getting a number that's below 0 or you're getting a number that's above 1, you did something wrong. So it's very easy to make mistakes in these, and it's very easy to make arithmetic mistakes here, so try not to. As a rule of thumb, a nice way to catch if you've made an order of operations mistake is if this is not centered around p hat, then you're guaranteed you made a mistake. Because you're adding and subtracting the same thing to p hat, whatever your interval will always be centered on p hat, will always be symmetric around p hat. So if you're not symmetric around your sample proportion, you did something wrong. So just a nice rule of thumb to keep in mind. It doesn't mean, if you are centered, it doesn't mean it's perfect, because there could have been a mistake in here. But more times than not, when I see people have the right setup but then have the wrong answer, it's because they messed up the order of operations. So be careful. It's an easy thing to mess up, but it feels really bad when you do. So careful. Yeah. So let's move on to examples. I've got 4 examples prepared, so 2 in the slideshow, and then 2 I'll move to a whiteboard to show. So here, the first example, pretty quick one. We surveyed 400 boat owners and found that 48 named their boat Serenity. Find a 95% confidence interval for the population proportion of people that named their boat Serenity. So here, we need n, p hat, q hat, and z sub alpha over 2. These are the things we need. We need n, p hat, q hat, z sub alpha over 2, and again, p hat. So, n, we surveyed 400 boat owners. We surveyed 400 boat owners. That's sample size. N's 400. P hat, here, we actually don't know what the proportion is straight off the bat. We're not given that information, so we need to find it. Well, we found that of these 400 boat owners, 48 named their boat Serenity. So that tells us what p hat is by simply saying, okay, it's that 48 that have what we want over the total sample size. So 48 over 400, which is 0.12. If p hat's 0.12, q hat's 0.88, just by definition, by the fact that q hat is always p hat 1 minus p hat. Finally, this is a 95% confidence interval. A 95% confidence interval will always have, if it's z anyway, it will always have a z score of, it will always have a z sub alpha over 2 of 1.96. You'll always use 1.96 for z. So we just plug this stuff in. We say, great, I've got 0.12 here, 1.96 here, 0.12, 0.88, 400. So we just put it all in. 0.12 minus 1.96 times the square root of 0.12 times 0.88 over 400. This root times 1.96 works out to about 0.032. So we get 0.12 minus 0.032 is less than p, is less than 0.12 plus 0.032. And this gives us our interval that we expect our true population proportion, the true proportion of boats named Serenity, to be within. So we expect that we're 95% sure, essentially, that that between 8.8% and 15.2% of boat owners name their boat Serenity, according to this problem. Awesome. So that's it. This is all we need. This is all that confidence intervals for proportion will do. It's the same exact idea as confidence intervals for the mean. It's just using proportions. So another example here. Suppose that in a certain election, candidate campaigner has received 57.6% of the votes after 5,000 ballots have been tallied. What's the 99.5% confidence interval for his actual population proportion of the vote? So when you see things like actual proportion, true proportion, these are all stand-ins for just population proportion. So great. You've probably seen things like this. If you've ever watched election coverage, you've probably seen that places will start putting up who's a projected winner after only a few thousand votes have come in, even though a state might have millions of people in it. It'll be like, yes, with 1/50th of the population reporting, we already know who won. Or we already think we know who wins. And this is actually not unexpected. This is very, very reasonable. What we're going to see here is at the end of this problem, even though we're looking at something fairly close to 50% and 5,000 ballots, which maybe occur in a state of millions, it's not going to matter how many people that state occurs in. It only matters that we surveyed enough. Or how many people live in that state, rather. How many people that state occurs in. Grammar. But it actually doesn't matter how many people live in the state. And what we're going to see here is we're going to be 99.5% confidence interval is still going to be pretty narrow at the end of this problem. So it's not unheard of to get an excellent idea of who's going to win a state or who's going to win an election or who's going to win, a popular vote without having anything like a meaningful amount of the population actually report in. So once again, let's actually go through this. First off, we need p hat, q hat, z, and n. P hat, well, 57.6% or 0.576 if you want to put it as a decimal, which we eventually need to do. If p hat's 0.576, then q hat's 0.424. It's what's left over. N remains the sample size, 5,000 ballots, 5,000. And z sub alpha over 2, that is the z-score for a confidence interval that needs to be 99.5% of all data. So that means that on either side of the confidence interval is an area of 0.0025 in the normal distribution. So that means that we are looking for the z-score corresponding to an area of 0.0025, which in the table we would find is negative 2.81. As always, we use the positive value instead of the negative, so we use z sub alpha over 2 is 2.81. So putting this into our formula gives p hat minus z times the square root of p hat times q hat over n, so 0.576 minus 2.81 times root 0.576 times 0.424 over 5,000. This square root comes out to 0.00699. Probably unnecessary for me to have gone out more than 0.007, considering what we're going to end up with anyway, but hey. Even if I say round to 3 decimals, when you're kind of in the middle of computation, you can round a bit further and it might save you kind of an off by 1 error later on. But I won't take off points for if you're off by like 1. I'll take off points if you're off by, if you're supposed to get, let's say, like 0.576 or 0.556 to 0.596, like we're going to get, and you get 0.456 to 0.696, you know, yeah, it's going to cost you, but like, you know, if you ended up getting 0.555 to 0.597, great, fine, same answer. So anyway, back to this. We get 0.576 minus 2.81 times 0.00699 less than p less than 0.576 plus 2.81 times 0.00699. And this gives us roughly 0.556 less than p less than 0.596. So we are 99.5% sure that Campaigner here is going to have a popular vote between 55.6 and 59.6% of all voters of all ballots. So if you've seen things where the news says, "Oh yeah, this is what this is going to come out to, plus or minus 1%," you know, yeah, they're saying that with pretty remarkable confidence. It doesn't. I mean, it takes a lot, 5,000 ballots, but compared to a population, it doesn't take that much to be pretty dang accurate on the grand scheme of things. I mean, you know, on a local scheme, 5,000 is a lot. So this is all we're looking at here. This is all we're kind of dealing with population proportions. It's just trying to make sure things go in the right place. So again, let's just switch over to one more thing that we're going to look at. And so here I've got two more problems. Going to have to handwrite this, so good luck to me. All right. I randomly surveyed 218 BA graduates and find 181 were from New England. Let's find the 95% interval, confidence interval for the true proportion of BA graduates that were from New England. So first off, what we need to do here is we need to find P hat, Q hat, and I'm not going to try and write the subscript alpha over 2 because, dear God, I'm having enough trouble writing with a mouse as it is. But we need these things. So P hat here. P hat's gonna be the number that we have that have whatever quality we want. That's 181. Oof. Over 218 over our total population. So, or over our total sample size rather. So, I'm going to make that approximately equals, I calculated this ahead of time. It is 0.83. There are too many 8s here, and it's difficult to write with a mouse. So, if P hat's 0.83, that means that Q hat is 0.17. We've already seen that's supposed to be a Q. We've already seen that N is going to be 218. And lastly, we end up getting that our Z, that's a Z, is going to be 1.96. And this is something we've seen plenty before. 95% confidence interval. That's supposed to be an underline. Let's try that again. 95% confidence interval. This is something that we've used a lot. A 95% confidence interval. If you're dealing with Z, it's always going to be a Z-score of 1.96. Never not. So let's set up the actual interval. So here it's going to be P hat. So 0.83. Whoops. Try that again. That's an 8. 0.83 minus my Z times the square root of our P hat, 0.83, times our q hat of 0.17 over our n of 218. And this is going to be less than p, less than our population proportion, this is kind of the low end of our interval. And then the high end of our interval is going to be this same thing, 0.83, but instead of minus, it's plus. And now it's the exact same thing, 1.96 times the square root. Let's make it a little bigger this time so I don't suffer quite as much. Oh, 8s with a mouse are so hard. 0.83, that's a times 0.17. And again, still in the square root over 218. Again, I've calculated this in advance. You're going to have to trust me when I say that the square root of 0.83 times 0.17 over 218 is 0.025. So what we end up getting here is 0.83 minus 1.96 times a little over 0.025, actually. It's going to end up being 0.83 minus, after we multiply by 1.96, we're just going to get 0.05. Less than p, less than 0.83, plus 0.05. So here, what we get is 0.78 less than p, less than 0.88. Now here, it just so happens that the way everything worked out, we didn't end up needing a third decimal place. This is 0.780, this is 0.880. That's not going to be the case with the next problem. So you'll see me go out to 3 decimal points in the next problem. So here, a sample, and this is it, by the way, we're done. Notice again, this is symmetric around 0.83. A sample of 600 MLS free kicks yielded a success, a goal rate of 7.5%. This is according to data from American Soccer Analysis. So I did not collect this myself, but it is real data. The article suggested they picked 600 free kicks chosen at random from about, I believe it said the last decade or so. Did not give an exact time frame, but if you're collecting data from the MLS alone, it's dubious how well that generalizes. So, you know, you're going to collect data in mediocre ways. It's just to make a point about local league, that's fine. You try and make a point about global league, this won't apply. But yeah, so let's take a look at what we expect what we would expect the population proportion for goal rate from free kicks in the MLS to be in general with 90% confidence. So once again, we need p hat. This time we're giving it for free. It's 0.075. Hooray for less 8s. We need q hat, but if p hat's 0.075, then q hat must be 0.925, just the opposite of 0.075, whatever's left over. We need n, but n is 600. It's just sample size. And we need z. I'm going to try the alpha over 2 here. We need the z, but the z-score here is the z-score for 90% confidence, which we know from past use or from looking in the z-table for a z-score relevant to an area of 0.05, or just from the bottom of the t-table. Once again, that it shows you the confidence intervals at the very bottom there. At any rate, that's a decimal. It's 1.645. is our z-score. So here, once again, we just fill the numbers in. So we get 0.075 minus 1.645 times the square root of 0.075 times, that's a 7, 0.925 divided by 600. All of that's in a square root. And once again, less than p, less than 0.075 plus 1.6454. There we go, that's a 6 now. 1.645 times that same square root of 0.075 times 0.925 over, wow, that's just the worst, over 600. Make that better, 9. All right, so once again, calculated in advance, what we end up getting here is our square root. This is about equal to 0.01075. Oof. I'll never understand how, like, some of the YouTube video editors actually manage to write things reasonably. I guess they're probably using an iPad instead of a mouse. But anyway, this is about equal to this is about equal to 0.01075. So here we just end up with 0.075 minus 1.645 times 0.01075 is less than p is less than 0.075 plus 1.645 times again 0.01075. Again, you could just calculate this all out in one string. It'll make it even more accurate than what I've done here, but either works. If you're off, again, if you're off by a thousandth, I'm not going to care in any particular way. Anyway, 1.645 times 0.01075 will give you 0.018, I believe. I'm going to double check that right now. Yep. So what we end up getting here is 0.075 plus or minus 0.018. Please try not to write the whole plus or minus thing. This is okay. I'm just doing it to save time and space because I think you can tell this is brutal enough. And this gives me a final answer of 0.057 less than p less than 0.093. So we are 90% confident that the actual success rate for free kicks in the MLS should be somewhere between 5.7 and 9.3%. Noticeably better than corners, I guess, but not particularly amazing. So yeah, that's about it. I just erased all of that, and wow, this whiteboard's terrible. I apologize. Please go back and freeze frame on the very end of that if you need to see it. Ah, there it goes. It comes back. Why is that? Oh well, just because web whiteboard, I guess. Yeah, so that's about it. for now, that's really all you need to know about population proportions. So yeah,